And okay, let's deal this one. This is the class notebook. You can follow it in a separate window, but also it's also shared over here. So we're talking about unit number 2. Okay. So first concept of unit number 2 is something called polygonal mesh. What is a polygonal mesh? Definition of a polygonal mesh is a set of polygons. All the times, or maybe all the times, we're going to use triangles. Okay. All triangles, for example, triangles. But there could be other ones. Okay. And the important thing is that encloses 3D space. This is very, 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 very important. Very, very important. If you are going to tell me just one single triangle or two, let me think. Triangle. Okay, 3D triangle. Okay. For example, this one. Oh, sorry. Yeah, this one. This blue one over here. We have like 3 faces. One face over here, one rectangle over here, another rectangle in the back part, another rectangle as a base. But 3 rectangles are not enclosing the volume. Okay, in this case it's volume. Encloses a 3D space as a volume. Okay, so the definition of a polygonal mesh is that it must encloses a 3D space. If it does not encloses a 3D space, we're not talking about a polymesh. Okay, so typical polymeshes, 3D polymesh, and also it's abbreviated as a polymesh, polygonal mesh. Let me write it down over here. It's the same as a polymesh. Okay, and it's just for describing that you could put together a lot of rectangles or polygons over here, and then the polygons are going to enclose something. Okay, the greater the number of polygons, you can enclose different complex shapes. Okay, so a lot of polygons means a lot of definition. Okay, fewer polygons, it's something called low polymesh. Something like that. For example, over here. Okay, over here we have this hat that has on the right side a lot of polygons and the left side fewer polygons, so you could see the difference. This is a low polygon count. Okay, so we're using a few polygons, a hundred of polygons, and you can see how you can resemble the same volume, almost the same volume, with different levels of polygons. Okay, different number of polygons could lead to different detail on the polygonal mesh. And also, it's very, very important to talk about the topology. For example, you could use thousands of polygons, like in this one, in the third one. And because of the polygons are kind of repeating surfaces and using in a bad way, you could rearrange the polygons, okay, with fewer polygons and optimize the polymesh, like in the first one. Okay, there are algorithms, there are metrics that uses the distances between the polygons and the distances between the original figure, so they could be optimized in the representation of the polygons. Okay, but basically for our course, we are just presenting what a polygonal mesh is. So a polygonal mesh is a set of polygons that encloses a volume. Okay, basically that's our definition. So what problems would be with this enclosing option, the enclosing description, is that maybe you will have some strange behavior like in this one, for example. Something like that is not enclosing things could be problematic. Like I don't know if you don't the clean bottle. This is very strange object. The clean bottle. Okay. Clean 3D clean bottle. Okay, this one. Clean, sorry, it's clean. Yeah, this one. For example, if you wanted to resemble this one as a polygonal mesh, you will find troubles, topological problems with this object. Okay, so because this object doesn't enclose a volume, or it encloses the entire 3D space, it's very difficult to work with this polygonal mesh. So it is called not a polygonal mesh. Okay, so if you are taking polygons and your polygons resemble some object like this one, this is not a polygonal mesh. It doesn't fit the definition of a polygonal mesh. Okay, it's a problematic object. So topological description of these objects are kind of different. So we are not working with that. We are talking with a traditional low count, low poly mesh. Okay. So we are talking about that one. Why low counting polygons? Because we don't have computational power enough to build those high polygonal meshes. Okay, with high count, count of polygonal mesh, we're talking about really lot of polygons. Let me over here. For example, 148 polygon and versus 2000, almost 2000 polygons. So you can see the difference, doesn't it? So you need plenty of computational resources to build or to draw that amount of polygons. Okay. So questions with the first definition of a polygonal mesh? Questions over there? No, no questions. Okay, that's it. So once we know what the polygonal mesh is, the next thing that we are going to work with is something called the vertex list format. Okay. What is a vertex list format? It's storing it's a structure for 3D polymesh storage. Okay. What's the description of this vertex list format of BLF format? Okay. We're going to have 3 different lists. So we need a list of vertex. We need a list of faces, sorry, a list of edges, and also a list of faces. Okay. So what is the idea? The list of vertex. List of vertex. Okay. The list of vertex are going to have the number of the vertex. Okay. And then you're going to have the x coordinate, the y coordinate, and the z coordinate. Okay. Let's add another insertion, insert below. Okay, that's it. So vertex number 1, I don't know, this would be the coordinates for x, coordinates for y, and coordinates for z. Okay. Vertex number 2, it's this one, maybe this one, and maybe this one. Oh, sorry. Okay, so we have another vertex because we need to build a triangle. Another vertex, 4 vertex, and so on. You get the idea, doesn't it? You need a list of all the vertices that are going to build the iMesh, the polymesh. Then so far with a list of vertices. Okay, next one is the list of edges. Okay, and that could be kind of easy, a list of number of edge, x, y, z. Oh, sorry. And then again, insertion below, insert below. Okay, then I would form an edge, the first edge. Okay, sorry, this is wrong. Okay, over here we have vertex 1 and vertex 2. Sorry. Okay, now it could be easier for me just to describe that the first edge is from vertex 1 to vertex 2. The second edge is from vertex 2 to vertex 1, so vertex 3. And the next one is the edge from vertex, the third vertex is from vertex 3 to vertex 1. Okay. What's the advantage of this one? Is that the list of vertices types are something like unsigned, integer, then double, double, and double. Okay. And now the list of edges are just unsigned int, unsigned int, and unsigned int. Get the idea? So if you want to describe a vertex, an edge, let me put together this one. You just have to tell me which is the reference to the list of vertices. Okay. And of course, the third level, the list of faces, that will be very important for this one. You just need this one, and I'm going to use just triangles. So if we use triangles, a triangle is made of faces. This is H1, H2, and H3. Okay. Right, build this one, insertion, and below. That's it. So over here we have that the first face is going to be built by H1, H2, and H3. And that's a triangle. Okay. The second one, I don't know, I'm going to start to get things strange over here, something like that, and so on. Question so far with the description of a polygonal mesh using the format, the vertex list formats? Questions so far? No questions? Okay, so let's make this exercise. This will be the exercise that you're going to find in the test. Okay, so the exercise is the following example. Okay, in the test, I want to ask you something like that. Okay, it's the same type of question that I want to ask you on the test. Okay, write the DLF format for a cube. Of course, I'm going to use different shape, but I need you to describe a cube. write the BLF format for a cube. Okay. Any questions about this this example? Do you know how to build the three lists, the list of vertices, the list of edges, and the list of faces for this cube? Is it clear? Okay. Yes, well.
First, we have to make the face for the up and the top of the cube, and then we have to make um, a face with the vertex of make of the this that part of the cube, top and bottom.
No, no, no. You have to write down a table with how many vertices?
8.
8 vertices. So you need to propose the x, y, and z coordinates for a cube. Do you get that idea?
Yes.
Okay. Then the next step, once you propose 8 of them, the 8 vertices, how many edges do you need to propose?
12.
Okay. It depends on the type of faces that you are going to draw. What type of faces you are working with? Which polygons you are working with?
Triangles.
Okay, if you are working with triangles, how many edges do you need? And there is not 12.
18.
Okay, do you see why do you need extra edges?
So you need between vertices in the square form.
Yes, because the shape of the traditional face for a cube is a rectangle, and we are not working with rectangles. We're working with triangles. So you have to put together two triangles in order to get a rectangle. Okay.
Okay.
Okay. So that's what you have to do in order to build a cube using these vertex list formats. Okay. Let me. Okay. You have to define the position of 1, 2, 3, 4, 8 vertices. Then you have to build the edges. And because you need 4 extra edges to join this corner to corner in order to build triangles. Okay? So that's what you have to do. So
Okay.
is there any question that you have to do in these type of examples?
No, I was thinking it was a rectangle form, but in triangle we have to change it.
Yeah, we are going to use triangles. Triangles. Okay, is it possible for you, if you have different project, to work with rectangles, but the rectangles are not stable forms on 3D. So the most stable and the minimum shape on 3D stable form is a triangle. Because if you define a rectangle, maybe the rectangle is not going to have this stability. Topologically speaking, the rectangle is not stable and the triangle is fully stable. So that's why we're using triangles. You get the idea?
Yes.
Okay. So on the test, I'm going to ask you to build, to write down the BLF format for a different shape. But you can practice with the cube. Okay. So you are going to tell me vertex 1, 2, 3, 4, 5, 6, 7, 8, and then the edges, and then the faces. Okay.
Okay.
So any question about this example? And any question about the vertex list format or what it's a polygonal mesh? Yes, David?
Hello.
Yeah, hi.
My question is, what do you mean by unstable in this context?
Okay, just imagine rectangle, rectangle. As you know, the rectangle is by definition, okay, let's talk about a 3D rectangle. The rectangle is going to be defined using 4 points, doesn't it?
Yes.
Okay, what happened if you miscalculated the position of one vertex of this rectangle? So if this 4 point is slightly moved open or down, what is going to happen with the surface?
It will be a little different.
How much or in what sense it could be different? Let me write something. What would be different? Describe me the difference that you're going to find if I move this point slightly up or slightly down. What would be the difference?
Um, we we will have like two triangles.
Yes, exactly. You need to deform, and somehow you're going to break the flat surface. And then at this point, you have to build the triangle. If you don't have triangles, you don't have flat surface. You get this image.
Okay, yes.
So that's the stability. You're not going to end it up with flat surface. Think less as a flat surface, okay? And if you
Okay,
have a
yes.
triangle, it's not possible. You can change the triangle positions, and you always are going to build a flat surface, a plane. The stability is because the 4 points are in the same plane. Kind of the mathematical definition is if the 4 points are on the same plane, then you have the stability. And if you do miscalculation on the 4th point, then you will have kind of a strange behavior. So that's why it's easier and stable to use just the triangles, because it doesn't matter which 3 points you're going to give me in the space. I must be able to build a plane that passes through all the 3 points.
Yes, now I understand. Thank you.
Okay, so that's why we are preferring to use triangles. So it's possible to use other polygons, but we are going to use triangles because this stability of this flatness of the surfaces. Okay, so any other question? So today's topic is about what is a polygon mesh, how to represent for storage or for manipulation, storage also for processing, this 3D information. So we're going to build this information over here, and you have to write a program, write a C program to convert available conversions OBJ into vertex list format. Okay, so the information is going to be stored in the OBJ. You're going to read the OBJ files, but we want to work with BLF. So we need to read information and write down the information in this format. So a list of vertices, then a list of edges, and then a list of faces. Okay. Questions with this program? Yes, Emilio?
So the output of this program will be three different, uh, um, in this case, TXTs that represent the BLF, or how do you like the output?
Okay, you need to define the BLF. define your BLF. I want to give you the openness of your own BLF. You could tell me that you're going to build 3 files. It's possible to do that. Okay, three different files. Also, the options. I will give you options. Option number 1, 3 different files. 3 different files. That's one option. Okay, another option, only one file or one single file. Okay, so in one single file, you're going to need to put together all the stuff in one single option. Okay, so different files, one single file. Also, with different one single file, you could use the ASCII. Okay, sorry, ASCII or binary version. I would prefer one single file binary. If you ask me, I will prefer, it's better to use binary single file. But it's possible also, if you are going to use 3 different files, to use ASCII format or binary format. It's also possible. So choose the one that you want. And if you ask me, the one that I will ask you to program is binary single file. But you have to define the structure, the order of what's going to be over here. One thing that you have to define on your format is, for example, and it's just an example of the structure. Example of this structure. One example would be, for example, the number of vertices. Okay. I don't know how to describe it. Okay, number of vertices, and then x, y, z, n times. I don't know. N is the number of vertices, and then this times n. I don't know if it's clear. And then again, the number of edges, and then h1, h2, I'm sorry, vertex 2, vertex 1, times m. This is another one. And finally, m and I don't know, p, or m and o, number of faces, and then there would be h1, this is vertex 2, h2, and this is h3, and this times o. This is m times, and this is o times. Okay, this is a very basic format that you could use. But use whatever you're more confident with. This is just an example. Okay. Another question over here? If just to read information and put the information in this structured BLF and write down in a file. I would prefer one single file, but it's possible to write 3 different files. And also the naming convention for the 3 files is completely up to you. If you're going to use this convention of 3 files, just use whatever works better for you. Okay. More questions about this implementation of the BLF? So it's two sides of this story. So what's polymesh? It's a typical question for the test. What's a polymesh? Second question is describe, I don't know, a pyramid. a basic rectangle-based pyramid. Describe this pyramid using BLF. So again, you have to describe the 5 vertices, the edges, and the faces. Okay, the same example as the cube. Then for the test, I'm going to use a different shape. And the third one, and the next step is to build a program capable of reading OBJ format and writing down the BLF. So that's when we are going to work with thousands or thousands of vertices. That's why we need a program because there's a lot of information to be processed. Okay. Also, this is the format that we're going to use, but there is plenty of other formats. There is one 3D storage format. 3D storage formats. 3D, oh no, 3D storage format, double wing. No, double wing, 3D format, no, just, that's it, okay. In this format, you are going to store twice the edge. So one edge is going to be stored in one direction, and the other edge is going to be stored in the other direction. Let me see if I could pull in edge format. Yeah, kind of this one with double representation. Let me see if we can see another one. No, edge. Well, double edge. 3D. Yeah, this one. When you have this representation over here, you are going to represent one edge in one direction and the other edge in the other direction. So you are doubling the space required to store a 3D object. There is some type of operations, there is some type of applications that requires that you build this type of structures of this type of representation of the 3D shape. Okay, we are going to use a simple one. We are going to use one single edge per shape. Okay, but this is also this half edge or double edge representation. Okay, so just for you to know that there are different formats, different structures for storing polygonal mesh, but we are going to use a very specific one. We are going to use BLF. We're going to I'm going to ask you on the test to write down Tom BLF and then to program Tom BLF. Okay. So questions so far? Okay. So next step. Once we know how to represent faces, okay, this unit we're going to put a lot of attention on faces. We need to draw solid faces. Okay. So how to draw solid faces? In order to draw solid faces, we have to remember that the line drawing algorithms so far are just for building the edges. So if I put together drawing over here, okay, I have this drawing stuff. Okay, now how to build, highlight, okay, draw. That's it, okay. So far, we have these vertex pixels over here. Okay, and if I told you that this is an X, Y, point, and over here we have another x, y point, and over here we have another x, y point. And I told you that this is my point 1, this is point 2, and this is point 3. If you apply the line drawing algorithms, okay, you're going to tell me, okay, this is the first pixel, this is the next pixel, this is another pixel, this is another pixel, and this is another pixel. Then this is another pixel, this is another pixel, another one, and another one. And finally, the third line is this pixel, this pixel, this pixel, this pixel. Okay, so far so good. You can build something like that. Okay, with point number 1, point number 2, and point number 3. You know that from 3D you can build this one by perspective projecting the stuff, and you can build something like that. Okay, questions so far? Okay, so what we have over here, okay, it's a list of pixels. Okay, so maybe this one, and I'm going to start trying to figure out things. Maybe this pixel is, I don't know, 10 and 10. Okay, this second pixel is slightly 11. Okay, and it's down, it's 9. Okay, so you're going to get the positions of all the pixels. All those pixels will have positions. For example, this one, I don't know, it's 9 and 9. You get the idea? So you're going to have a list of pixels. Over here, let me move this together. So you will have a list of pixels. Some pixels are for line 1, and other pixels are for line 2, and another set of pixels are for line 3. So 3 times Bressenham algorithms are going to end it up with something like, I don't know, 9, 2, 10, 3, 11, 4, I don't know. And this one, this would be 8, 3, and 8, 2, and maybe this is 8, 1, and maybe this is 8, 4, and so on. Okay, so what I need now is to calculate this pixel, and this pixel, and this pixel, and this pixel. You get the idea? I need to calculate the intermediate pixels. Okay, we are going to call this algorithm the scan line algorithm. Sorry. Okay. So right down over here. Yeah, we're going to call this a line. So scan line algorithm. Algorithm. Okay. What is the idea? Very basic idea. Let's switch to drawing. Okay, very basic idea. You have X, Y coordinate system. Okay. Then you have a triangle with the endpoints over here. Okay. So the idea is that you're going to have this. It could be a scan line from top to bottom, bottom to right. I'm going to use this one. And this is going to be my scan line. And this line is going to be start over here, and it's going to be moved up. Sorry. And it starts to be moving up the scan line. What I want for this scan line, I want this scan line to get those points. Okay, and this is the minimum, and this is going to be the maximum. And once I have this minimum and this maximum, I just have to build a for loop for mixing all the points together, for calculating the points over here with a single for loop. This is a for loop from the minimum to the maximum. Of course, the pixel minimum and the pixel maximum you don't need to calculate, so it's kind of open interval over here, to the minimum, to the maximum. Okay. And once you get the information, I don't know, for I don't know, y equals to 10, then you need to build the same 1 equals to 11 and y equals to 12, and previously you have calculated y equals to 9. So basically you are going to have the line moving, calculating the pixels, calculating the pixels, calculating intersections, minimum, maximum, the pixels, minimum, maximum, the pixels. And that's how you are going to fulfill. The idea is that we need to fulfill pixels. In this case, we're going to build a solid face. Sorry. The idea is that we need a solid face. Okay. Question so far? This is the scanline algorithm. So what you're going to receive as an input, you're going to receive the list of pixels. Which pixels? The pixels that build 3 lines. Why 3 lines? Because we want to build triangles. Where are you going to take the triangle? You're going to take the triangle for each entry of the list of faces. The face is going to tell you which edge you're going to start with, and the edge is going to give you which vertices you're going to work with. And the vertices is going to tell you the XY coordinate that you're going to use. So as you can see, there's a lot of steps that you need to go throughout the process, from the reading of the information, the edges, the faces, the storage of this one, and then applying this solid face drawing, in this case the scanline algorithm, to resemble which pixels are going to be in the middle of the face. Okay, so basically this is scanline. The scanline could start in the maximum y coordinate, and then goes from the maximum y coordinate to the minimum y coordinate. Okay, there is also possible that the scanline works on x-axis, and so from left to right, and or right to left. Okay, but whatever it works for you, it's good. It's just to set up a line and then move the line along the face and this scanline fashion. And the scanline objective is to calculate the intermediate pixels that goes over here. So fulfilling pixels are going to be to draw a solid face. Questions so far? Yes, Marco Antonio.
Hello, Prof.
Hi.
Can you hear me?
Yes, yes.
We save fulfilled pixels in a new list.
Exactly.
Okay.
Exactly. That's the idea. That's the idea.
Thank you.
You're going to end it up with this scan line. You're going to end up with a list of pixels from different origins. Okay. For the edges, those are the pixels on the edges, and also the list of pixels that are inside. Okay. So if you put together those edges and inside a list of pixels, then you can build all the shape over the line, all the pixels over the line, all the pixels over the line, and then with the other list, you can put pixels over here. Okay? That would be interesting to change the color so you could see objects displayed. For example, if you displayed a cube with something like that, you could see lines over here, sorry with it by the drawing, lines over here, and then you can see pixels in the middle. I'm sorry, I use different ones. Okay, the idea is the edges are going to be on green. Okay. I will try to do better drawings. Sorry. This is this one, this one, this one, this one. Okay, so on. And the pixels in the middle are going to be something like that. As you could see, there's the first problem. If you draw first this one, then the next moment that you draw this one, the pixels are going to be overlapped. Okay, you will solve that problem, but right now I want to see that I want to show you what happens. The order of the this is the first one, and maybe this is the second one, and you're going to be ended up with a shape over here, and depending on the order, you're going to see that something wrong happens with the edges. Okay, at least the minimum edges that you're going to expect it to see is the edges of the shape, because nobody is going to go over this one. Nobody is going to be over this one. Okay, so these pixels are going to be in the same color, no matter what. But what happens with the intermediate ones depends of the order of the drawing. So we have to take care of this, but it will be next class. I know that for this class you are getting enough conceptions and things to do. Okay. So is it clear? The list of pixels per face could be divided into the pixels that build the edges and the pixels that goes inside. Also, is it possible to join together the two lists so we have one single list of pixels? It's also possible. But if you want to look what's happening with this effect, paint them with different colors. So see what happens. And it's very interesting to look at. Okay, more questions? So is it clear this practice, what we are expecting? Okay, good. So it could be that all for today, because right now you have two programs to work with. So remember, there's the concept, and there we have two programs. Write a C program to do the conversions. The first one. First thing that you have to do. Oh, sorry. This one. Write a C program. And the next thing that you have to do is write a C program to display solid faces for OBJ. Okay, so now that you have your written OBJ, now I want the OBJ to be displayed with solid faces. Okay, so we're going to line drawing the edges and then calculate the intermediate pixels with this scan line. And the scan line is going to give you the list of pixels in between, and now you can build solid objects. That's the idea, solid faces. We have to work with the order and occlusion, something like that, but that will be in the next class. For today, just 2 programs. The first program to work with the BLF formats, and the next one is to use solid faces for OBJ. And this program, this one, okay, internally uses BLF. Okay, this is very important. That's why we are going to introduce the BLF, because from this practice and now, all the consecutive practice from this one needs to use internally the BLF format. Okay, that's why we are introducing the BLF. Okay, questions about those 2 programs that you have to build, to write down? Any questions? Okay, also in the test, I could ask you to calculate by hand the pixels over here. It's a typical problem. I think it's very easy. I will give you 3 points, and you have to Bressenham for this, to apply Bressenham from this line, Bressenham from this line, Bressenham for this one, and then you have to calculate the pixels over here. It's kind of easy, but also you have to do it, okay, at some point. So first try to do it by hand, this one first, and then to program it, and then to see with large files and see the shape of the files. Okay. If you use the same color for the edges and for the inside pixels, you're going to end up with these shadow objects, because there is a solid object. You will find out a shadow. That's also interesting drawing. Use the same color for the edges and for the internal pixels, and you will be ended up with a shadow image, okay, of the 3D object. You couldn't see the edges. For example, imagine what will happen. Okay, it's a typical 3D cube. Okay, over here in this typical cube, you could see the faces because the faces are drawn with different colors, slightly different color. For example, over here, observing. You could see different color for each face. Okay, different gray level. We are not reaching that part so on. So if you if you use the same color for all the faces, you are going to get just the shape of the 3D object. Something like, I don't know, we don't have examples over here. As you could see, we can perceive the 3D-ness of the cube because there's different colors or different stuff for each face. But if the face is on the same color without these separations over here, we are just going to perceive an hexagon. Do you see? And that's shape, shadow. No, not shade. Just like this. Just black over white shape. Okay. Okay. Questions so far? Okay. So start working with the 3D programs, with the concepts, and that's all for today's class. You have the notes on the class notebook. Okay, so you have the drawings, you have what you have to do. So see you next class. That could be all for today.
Thank you, Prof.
Yeah, see you.
See you.